long time now. And Matt, so thank you very much, Matt.
All right, thanks, Andika. It's a privilege to be here at this event honoring Professor Smale on his 95th birthday. Happy birthday. I'm going to tell you about his legacy for asymptotic stability theory and the impact his work has had in some of my work funded by the AFOSR. So what is asymptotic stability? So first, just to make my life simple, all maps in this talk are going to be at least continuous, and if you see a finite dimensional manifold or pair of those and maps between them, then everything is smooth, including the vector field on this slide. So what's asymptotic stability? Well, let's first consider a vector field F on Euclidean space Rn and an ODE x dot equals f of x, and consider an equilibrium point E, which is just a point that's a zero of F. And we say that E is asymptotically stable if, first of all, every solution of the ODE converges to E as time goes to infinity. And also if for every neighborhood of E, there's a smaller neighborhood such that if you start in the smaller neighborhood, you stay in the bigger neighborhood for all future time. So what I actually just defined is global asymptotic stability, and to make my life simpler, I'm just going asymptotic stability will just mean global asymptotic stability in this talk. So why care? Well, for the purpose of applications, asymptotic stability models a particularly nice kind of robust steady state behavior, and in fact, engineers try to achieve this through feedback control. So let me just show you one example of this. This is a YouTube video from Russ Tedrig's group. So here's a double pendulum. It shouldn't be able to balance upright, but through sensory feedback control, you can make it do that. Okay, so that's one particular feedback controller for that system, but a natural goal you might have is to design a stabilizing feedback controller that depends on parameters. So you have a parametric family of controllers with the idea being that later you can adjust these to create your desired transient response as you're converging to the steady state, say after you get perturbed away from it. This begs a natural question. Suppose we've already done this for some of the parameter space. We've designed a partial parametric family of stabilizing controllers. When is it possible to keep going and extend your choice over the entire parameter space? You might think that this is obviously possible, and in fact it's not. So it turns out that the answer to this motivating question depends only on topological properties of the space of all asymptotically stable vector fields on Rn, equipped with a very natural topology. It's the topology of convergence on compact sets, uniform convergence on compact sets of not only the vector fields, but also all of their derivatives. It's called the compact open C infinity topology. And the main theorem that I claim answers the question, and I'll explain why, is that if your state space dimension n is not 4 or 5, then this space of all asymptotically stable vector fields is not only path connected, but it's simply connected. And in fact, if n is less than 4, it's weakly contractible. So path connected means you can interpolate between any two of these vector fields. You can find a path between them. Simply connected means if you look at any parametric family of these vector fields parametrized by a circle, you can parametrically deform all of them to the same vector field. Weakly contractible means the same thing, but instead of a circle, you use a sphere, and the sphere can be any dimension. So this theorem, together with some obstruction theory and some smoothing theory, actually tells you what can be viewed as a boundary value problem existence theorem. So consider any compact manifold P with boundary, and consider any partial family F partial of asymptotically stable vector fields parametrized only by the boundary. Well, you can always extend that partial family to a family parameterized by the entire parameter space, at least if either n is less than 4 or n is greater than 5 and the dimension of your parameter space is less than 3. You might ask why these weird dimensional restrictions. Just to convince you that they seem to be necessary, if the path connectedness portion of the main theorem were true for n equals 5, then that would imply the smooth 4-dimensional Poincare conjecture, and nobody knows if that's true. So here's an example of these boundary value problem. So here I have a 2-dimensional parameter space, and I'm also saying, let's say state space is 2-dimensional. So here I have a family of asymptotically stable vector fields. So here's one over this parameter value. Here's another one over this parameter value. As you can see, they have very different transient behavior as they converge to the equilibrium point. And because these dimensions satisfy the conditions on the previous slide, it's always possible to extend this family, which is just over the boundary, to a family over the entire parameter space, but I can't draw that because I don't have enough dimensions. Here's another example that I can draw, and this example is relevant to a question asked by Charles Conley. So the question Conley asked was, I won't define all these terms, but when are isolated invariant sets having the same Conley index related by continuation, whatever that means? So a partial answer is actually given by a case of this boundary value problem. So if you have two asymptotically stable vector fields, you can always connect them by a path, and asymptotically stable equilibria, in fact, have the same Conley index. It's the zero sphere. And so we have an answer, at least if the state space dimension is not 4 or 5, as long as the sets are asymptotically stable equilibria, then the answer to Conley's question is always, and moreover, the continuation can be taken not just through any vector fields with isolated invariant sets, but through asymptotically stable vector fields in equilibrium.
That's particular to working on Rm, isn't it? Or can it be for any manifold?
Well, it's so I didn't say on the slide, but by playing with cutoff functions, you can make this a local answer, and then it works on any manifold. Yeah.
I see.
Yeah. Oh, thanks. That's a good question. So it's just a couple other quick applications. The first one you can think of as being a parametric Hartman-Grobman theorem, where you don't need hyperbolicity, and in fact, deviating from my earlier stipulation that everything is smooth, you actually only need the vector fields to be locally Lipschitz here, or continuous with unique trajectories. So if you have two parametric families, both asymptotically stable for each parameter p, then you can actually find a continuous family of homeomorphisms parameterized by the same parameter space, identifying trajectories of one vector field with those of the other under these dimensional restrictions. And so you can take GP if you want to be a constant family of linear vector fields, and then you can see why it's a parametric Hartman-Grobman theorem. One last application I'll just say something about. So if there's a natural space containing the asymptotically stable vector fields, I call them the almost non-singular vector fields. They're those having exactly one equilibrium. So it turns out, I'm not going to explain, but there would be an extra term here without the main theorem. The main theorem implies this extra term vanishes, so it's not shown for these dimensional restrictions. So you get information about these relative homotopy groups. What that tells you about is when it's possible to continuously deform certain families of almost non-singular vector fields into asymptotically stable families. So the outline of this talk, we already did parts 1 and 2, motivating question and answer, other applications. The purpose of this event is to honor Professor Smale, so that forces me to talk about the proof of the result. And what I want to do is try to sketch that and highlight the really crucial contributions of Professor Smale along the way. So step 1 will be to reduce our problem from a space of asymptotically stable vector fields to a space of Lyapunov functions. Step 2 is to then further reduce away from the Lyapunov functions to something I'll call a nonlinear Grassmannian. Topologists also call this the space of unparametrized disks. And then step 3 will be to study the topology of the nonlinear Grassmannian. And let's get started. So the first step is just one slide. So I'm going to sidestep telling you really what Lyapunov functions are. And I'm just going to define, so it's a global version, space of Lyapunov functions. That's what I'll call them. But these are just proper functions, also known as radially unbounded functions on Rn, a non-negative. They've only got one critical value. It could be, it's only got one critical point. The value at that point is 0, and that point has to be a minimum of the function. So we'll also equip this space with the compact open C infinity topology. And I'm going to consider this subspace of functions where the minimum happens at the origin. So, so it turns out that this space where the minimum, the subspace where the minimum is at the origin, essentially just by translation, that's the same up to weak homotopy equivalence with the space of all Lyapunov functions. And then the space of all Lyapunov functions is actually the same up to weak homotopy equivalence to the space of asymptotically stable vector fields. In fact, there's a weak homotopy equivalence given from this guy to this guy, which is just take the negative gradient. And the fact that it's an equivalence follows from Wilson's converse Lyapunov function theorem. So this proposition tells us that instead of studying S of Rn, we actually just need to study L0 of Rn. So what we need to prove is this theorem, which is the same as the theorem I showed you earlier, except now we have L0 here instead of S. Okay, so now I'm going to try to punt again, and we're going to move away from L0 to a different space. So here's the plan. And one piece of history is that Wilson, he studied the topology of level sets of Lyapunov functions using the dynamics of asymptotically stable vector fields, and we'll do some of that analysis on the next slide. But to prove the main theorem, after the next slide at least, we're actually going to turn that idea on its head. Instead of studying level sets using dynamics, we're going to use level sets of Lyapunov functions to study the space of all asymptotically stable vector fields. We'll actually use sublevel sets, but they are equivalent here. So, so here's a proposition telling us about not only the topology of level sets of Lyapunov functions, but the topology of sublevel sets. So it says that if the state space dimension is not 4 or 5, then for any of these Lyapunov functions, any sublevel set, I'm using the one sublevel set just as a choice, any of those is diffeomorphic to the standard n disk, the standard unit disk inside Rn. And the proof of this uses the flow of the gradient of our Lyapunov function to collapse continuously the sublevel set onto the minimum, and then collapse all of Rn minus the minimum to the one level set. So it turns out that tells us that the sublevel set is a contractible manifold with boundary homotopy equivalent to a sphere. And then for n not 4 or 5, that actually tells us that the sublevel set is diffeomorphic to Dn. So for n1 and 2, this is a classical fact. For n3, this follows from Perelman's solution to the 3D Poincare conjecture. And then for all n bigger than 5, so most n, follows from Smale's H-cobordism theorem mentioned earlier. Okay, so now that we know Lyapunov sublevel sets are disks for most dimensions, I'm going to use that information. To do that, I'm going to define this space here. It's the space of submanifolds of Rn diffeomorphic to the disk, known as a nonlinear Grassmannian, and topologized as this quotient topology, space of embeddings mod the natural right action of the group of diffeomorphisms on that space. It's a natural topology. And the open subspace consisting of those disks which are also neighborhoods of the origin. They contain the origin in their interior. So because we know sublevel sets are disks, the previous slide gives us a well-defined, what I call sublevel set map, which sends a Lyapunov function to its one sublevel set. So if we view the function as represented by its contour plot, This is the input. The output is just this blob, the one sublevel set, which is diffeomorphic to a disk, just a wobbly disk. So the reason we're interested in this map is because it's a weak homotopy equivalence. So we can go away from this space to study this space. And in fact, it's not just a weak homotopy equivalence, it's something stronger. It's a fiber bundle with weakly contractible fibers. So the proof of this, continuity follows by an implicit function theorem argument, the version for Banach spaces. Surjectivity follows by the disk theorem of Cerf and Pillay, and that's also the disk theorem implies that the base of this, the codomain of this map, is path connected. We'll need that. And then to construct local trivializations, what you can do is you can take any element M of this set, of this space, and you can construct a neighborhood U and a map from that neighborhood into the diffeomorphism group of Rn, such that for any n in that neighborhood, psi of n, which is a diffeomorphism, maps M to n. And then what you can do is you can use these diffeomorphisms to pull back Lyapunov functions. So you can send all of the Lyapunov functions in this preimage to Lyapunov functions in this fiber. So F is what I'm calling the fiber over M. And you can just check, I'm not showing it here, but you can check that that's a homeomorphism. So this map P comma F is a homeomorphism, local trivialization, which means by definition this is a fiber bundle, a topological fiber bundle. And it remains only to show that the fiber is weakly contractible. So because the base of our fiber bundle is path connected, we only need to check one fiber. I might as well make my life as easy as possible. So I'm going to check the fiber over the standard disk. And in that case, my fiber is just all functions with smooth functions with a unique critical point, unique minimum, and whose one sublevel sets the standard disk. And then it's kind of intuitive. I'm trying to show here that if you have, so here's such a function. It's got, see, there's a perfect circle there showing that its one sublevel set is, so this is the unit circle, unit sphere in higher dimensions. One sublevel set's the unit disk, and you can just kind of part the C away from that level set and replace the C with level sets of the function x squared to get the function x squared. You do create a singularity at the origin, but you can flatten things out so that it doesn't matter. And then, in fact, you can do this parametrically. So it actually shows that the fiber is weakly contractible. Okay, so now we know space of asymptotically stable vector fields, same as space of Lyapunov functions, same as space of this nonlinear Grassmannian of disks, up to weak homotopy type. So now we just need to study the space of the nonlinear Grassmannian. We already used Smale's H-cobordism theorem. We're going to use another result and the solution of a conjecture of Smale to do that. So it doesn't really make my life easier, except I'd like to not write a subscript if I don't have to. So that's basically by translation, GR0 is the same as the entire nonlinear Grassmannian. So I'm just going to drop that subscript. So to prove our main theorem, we just need to show that the appropriate weak homotopy groups of this guy are trivial. Also, to simplify my life a bit, I'm going to work with positively oriented orientation-preserving things. So EMB plus, diff plus, those are positive orientation-preserving embeddings and diffeomorphisms. So it turns out that there's a natural quotient map from embeddings to the Grassmannian, which just sends an embedding to its image. And this is a fiber bundle with fiber, the diffeomorphism group, orientation preserving of the disk. So in particular, it's a Serre fibration, so you get this long exact sequence of homotopy groups of a fibration. So each of these are groups. Each of the arrows is a group homomorphism. And what it means to be exact is the image of each arrow is equal to the kernel of the next arrow. So this long exact sequence, if I add more terms, it contains this segment for general K. So I don't have time, but I claim it's not hard to show that basically Gram-Schmidt orthonormalization, if you can believe it, shows that these arrows are surjective. They're group epimorphisms. So exactness, well, if this guy is surjective, its image is everything, so the kernel of this guy has to be everything, so it's the zero map. So it's the zero map, its image is just zero, So the kernel of the next map is 0, so the next map's injective. So we get that information. And this sequence is shown again here. And now if we consider this sequence for k equals 1, so this becomes pi 0 here, we can deduce that pi 1 of this guy is 0, which means that GR is simply connected for all n bigger than 5, because in that case, pi 0, which was this term, is trivial by the Cerf pseudoisotopy theorem. And so now the only thing left to do is we need to prove that GR is contractible when n is less than 4. And to do that by exactness, it suffices to show that these surjections are actually bijections in this case. So those surjections are induced by the top arrow in this diagram, which is commutative, and the diagonal arrows are just evaluate the derivative at a point. Which point? It doesn't matter. So this right arrow is a weak homotopy equivalence basically by zooming in. I don't have time to sketch that though. So it suffices to show by commutativity and this weak homotopy equivalence that this left arrow is a weak homotopy equivalence for n less than 4. That arrow is actually homotopic to this composition where you take a diffeomorphism of the disk, you restrict it to its boundary, and then you adjoin the value and derivative, let's say at the north pole of the boundary, which is the n-1 sphere. So this is the composition, and what we need to do now is for n less than 4, prove that this composition is a weak homotopy equivalence. What we'll do is we'll eliminate this first term, so we'll only have to show the same for f. To eliminate the first term, so the first term by a result of Cerf's first fibration theorem is actually a topological fiber bundle. Its fiber over the identity, for example, is the subspace of diffeomorphisms of the n disk that restricted the identity on the boundary of the n disk. Okay, well, what the heck is the topology of that space? Well, so for n equals 1, it's actually not hard to prove that that is contractible by convexity, a convexity argument. But for other n, this is hard. For n equals 2, this is a beautiful theorem of Smale. The proof actually uses the Poincare-Bendixson theorem that this guy is contractible for n equals 2. And then for n equals 3, it's contractible by Hatcher's proof of the so-called Smale conjecture. The conjecture just states that this is contractible for n equals 3. Or at least is equivalent to that. So rho is a weak homotopy equivalence. So now we just need to show that f is a weak homotopy equivalence for n less than 4. This is trivial for n equals 1. So we're just going to show it for n between 1 and 4. So by the way, sorry, I didn't say GL plus n is just the space of matrices with positive determinant. That space is the same thing as the positively oriented frame bundle of the tangent bundle of the n-1 sphere. And our map F, which remember was adjoining the value and the derivative at a point, factors as the composition where you take a diffeomorphism of the sphere, you restrict it to the closed upper hemisphere, then you further restrict it to the open upper hemisphere, and then you take that restriction and you adjoin the value and derivative. Restricting doesn't change the value and derivative. I'm not showing it here, but these are sort of standard and not too hard to show weak homotopy equivalence is the latter two arrows. So that means to show f is a weak homotopy equivalence, we just need to show that this first arrow is. But just like the last slide, the first arrow is a fiber bundle by the same result of Cerf. And now the dimensions get shifted by 1, so we don't need Hatcher anymore. This fiber is contractible by convexity and this beautiful result of Smale. So this whole thing is a weak homotopy equivalence, and we're done. So this completes my rapid sketch of the main theorem. And I just want to thank you all for your attention. This talk is based on this preprint, and if you're interested, my slides are available at my website. Thank you very much.
The problem for 4 and 5 is technical, you have a counterexample, or it's just that you need a different proof?
All I know is that my proof doesn't work, but I know that if for n equals 5, it would imply the smooth 4-dimensional Poincare conjecture. for the path connectedness portion. So it's at least hard, yeah, if it's true.
So you could get, how old are you?
34.
He's got time, he's got 6 years. 6 years, man. Funding's cut off.
I have no clue how to approach it. Yeah.
So, Matt, I'm just making sure I understood what you said about the Conley index. Are you saying if you have two vector fields, say, and then invariant sets with the same, say you only have one kind of isolating block in the Conley index, then you're saying you can deform one vector, you can isotope one vector field to the other to get from one? Is that what you said, or?
I can only do it for asymptotically stable equilibria, and I'm not saying I can isotope them, although I'd have to think about that. I can just homotope them, but through asymptotically stable vector fields.
So those invariant sets would have to be asymptotically stable.
And equilibria. There's work from 1992 by Reineck and Duke that treats the more general case of compact invariant sets, and he uses like techniques like Smale's handle manipulation techniques to get some results that are sort of more general, but interestingly don't cover the version that
You're interested in.
yeah.
Okay, thanks.
Thank you, man.
Thank you.
Our next speaker is Mason Porter from UCLA, and Mason, you use your computer.
Yeah. And I think, yes, yeah, well, that's